we'll continue with our curve sketching analysis here, and this was the first derivative of the function we're going to try to sketch the graph of in a few minutes. And what we want to do next is we want to determine where the graph's concave up, concave down, and if it has any inflection points. And all of those things are going to be able to be determined based on doing an analysis of the second derivative for this function. So if we take the second derivative of this function in its current form, I'm going to have to use the quotient rule to do that. So I'm going to do the derivative of the numerator, and I'm going to copy my constant into that derivative, and then the derivative of e to the 1 over x squared. That's actually going to be e to the 1 over x squared times the derivative of the inner function, which is negative 2 x to the negative third. So we did the derivative of that once already in the first derivative, so we won't really take as much time to discuss it here. But there's the derivative of the top. We're going to multiply that by the original denominator, which is x cubed. We're going to subtract from that the original numerator. Now I notice this is going to be minus a negative, so I'm just going to change that to addition. So here's the original numerator, and then times the derivative of the denominator, which is going to be 3x squared. So kind of an ugly second derivative. There's the numerator of it, and the denominator of it is going to be this denominator squared. So when you square something that's cubed, that's power to a power, you're just going to multiply those powers together. So let's try to clean this up a little bit. The first thing that I notice right away between this term here, if I take the product of x to the negative third and x to the third, those are actually going to cancel. So that's actually very, very nice that that happened. And then I notice I have a negative 2 times another negative 2. So I'm going to be able to rewrite that numerator as positive 4 e to the 1 over x squared. And then, let's see, this piece doesn't really simplify too much. I can multiply my 2 and my 3 together, and I can rewrite that as 6. I'm going to put the x squared next, and then the e to the 1 over x squared last. And that's all going to be over x to the 6th still. So we want to figure out when this second derivative is 0 and figure out when the second derivative is undefined. The only time the sign of the second derivative can change is if it's first 0 or undefined. So when we set the second derivative equal to 0, when you have a fraction and you're considering when the fraction might be equal to 0, all you're going to have to do is set the numerator equal to 0. So you set this numerator equal to 0, and you're going to probably be a little intimidated by this initially, but what you should always do if you can is try to solve by factoring. We do have a common factor of 2 between these numbers, and then also this e to the 1 over x squared is a common factor. So I'm going to factor out a 2 e to the 1 over x squared from this term, and when I do that, that's just going to leave me with a positive 2. And when I factor it out of the second term, I'm going to be left with plus 3 x squared. And so now you have this factored. You're ready to set this equal to 0, or set each factor equal to 0. Well, 2 is never 0. E to the 1 over x squared set equal to 0. I think we experienced this in the first derivative too. Natural log of each side is going to give you 1 over x squared equals natural log of 0. What's natural log of 0? It's undefined. You don't get a solution for that. I think something similar is actually going to happen if we set this factor equal to 0, because think about what you're going to do. You're going to subtract 2. You're going to divide by 3. And now you're going to say, okay, now I'm ready to do the square root of both sides. How are you going to do the square root of a negative and get a real number? Well, you're not. So we actually have to consider the second derivative being equal to 0, but we don't get any solutions from it. The second derivative is going to be undefined at the same place where the function was undefined, and that's at x equals 0. You know, look at this denominator. It's obviously 0 when x equals 0. This is undefined when x equals 0. This is undefined when x equals 0. So the second derivative is clearly undefined when x equals 0. So the only time the sign of the second derivative can change is as we cross the x value of 0. Now we're ready to go ahead and do our sign chart. Get my second derivative on the screen here. That should work. So my number line for my sign chart is going to have a hole poked out of it at 0 again. Function's undefined at 0. That is the only x value where the sign of the second derivative can change. If we want to pick a test value from over here, like negative 1, look at this numerator. You put negative 1 there, square it, positive. Negative 1 there, square it, positive. Negative 1 there, square it, positive. You're adding together two pieces that are positive. That's going to give you a positive numerator and then you take -1 and put it in place of this x and raise it to the 6th power, and you get a positive answer there. Now on the other side of 0, pick a +1, put it in place of all the x's. Everything's going to be positive, so you're looking at a positive second derivative for the entire graph except at 0. That means our function's concave up to the left of 0 and then also to the right of 0. Remember that at 0 we had an asymptote. So we'll go ahead and we'll fill in the rest of this list, and we'll see if we can put it all together to sketch a graph. So I've already filled in the part of this that we could have based on our analysis done in the first part of the video. Where are we concave up? Well, we're concave up to the left of 0 and to the right of 0. We're never concave down. We don't have any change in concavity, so we don't have any inflection points. Last thing I want to try to do before we try to sketch a graph of this function is I want to see if we can determine any obvious x-intercepts or y-intercepts. So graph is going to eventually go here. Do we have any y-intercepts? Well, think about your y-axis. On the y-axis, x is 0. What happens with this function when x is 0? Well, put 0 there, you're undefined. So we don't have any y-intercepts. Remember, that was actually our vertical asymptote, x equals 0 was. So no y-intercepts. Do we have any x-intercepts? Let's see, I don't think we're going to have any of these either. Right? You set this equal to 0 right on the x-axis. For an x-intercept, your y value would be 0. Natural log of each side is going to give you the natural log of 0, and you don't get anything. So we don't want to cross either axis here. So let's see if we can put all this stuff together to sketch a graph. What I typically start with when I have access to them are these limits that I checked for the asymptotes. So I noticed that on the bigger side of 0, my y value was positive infinity. So on the bigger side of 0, my y value needs to be positive infinity. On the smaller side of 0, as we approach 0 from the smaller side, the y value also has to be positive infinity. So my graph's going to have to go up off the page here, up off the page on that side too. As we approach positive infinity, we had a y value of 1. So I'm just going to plot my horizontal asymptote, y equals 1. And when x approaches positive infinity, my y value has to be really, really close to that asymptote. So I'm going to be here. I'm going to therefore end up just above that asymptote. Similarly, as we approach negative infinity, we got a y value of 1, or a limit of 1. So I'm going to have my graph be just above that asymptote over on the left edge as well. So I'm just going to try to sketch my graph here and see if it works out okay. So I'm thinking my graph is going to look something like this to the left of the y-axis and something like that to the right. It's kind of hard for me to hit that point there. Let me get rid of that. This graph was supposed to be symmetric, so I think I did an decent job of showing that here. Is everything else satisfied? Are we increasing from negative infinity to 0? Negative infinity to 0, yeah, our graph has positively sloped tangents. On the interval 0 to infinity, we have negatively sloped tangents. We're definitely decreasing. We don't have any maxes or mins on our graph. We are concave up on this piece of the graph. We're concave up. We're cupped upward on this piece of the graph. All of these other conditions seem to be satisfied just by being careful with the asymptotes and the limits that we check to determine them, and using those to kind of guide our sketch. So there is an example of how you would do this analysis if your function is an exponential function.